The Physics of Interstellar Travel. Chapter 2. Why travel to the stars? There are diverse motivations for sending an uncrewed spacecraft to a nearby star, both scientific and non-scientific. In this chapter we look mostly at the scientific cases. I also give a brief survey of the nearest stars and the planets around them. The fundamental advantage of studying a star system using an interstellar spacecraft, compared to studying it from the Earth, is proximity. The best achievable spatial resolution of a telescope is set by its diffraction limit, which is of order lambda r over d, where lambda is the wavelength of light, r is the distance of the telescope from the source, and d is the diameter of the telescope mirror. The ratio of the spatial resolutions achieved by two telescopes, label 1 and 2, of different sizes and at different distances from the source is therefore r2 over r1 times d1 over d2, assuming they're working at the same wavelength. Let's assume these two telescopes both want to observe a planet in the Proxima Centauri system. Telescope 1 is a 100-meter telescope on the Earth, so the distance is 270,000 AU. Telescope 2 is a 10-centimeter telescope on a spacecraft observing from a distance of 0.1 AU. The resolution of the telescope on the spacecraft is therefore 0.1 over 100 times 270,000 divided by 0.1, or 2,700 times larger than the resolution of the telescope on the Earth. This will give the telescope on the spacecraft a spatial scale of 0.023 Earth radii, which is of course enough to map the surface of an Earth-like planet. We could probably navigate the spacecraft nearer to the target than say 0.1 AU during a flyby, and orders of magnitude nearer if the spacecraft went into orbit around a planet. The second benefit of proximity is light gathering power. The light gathered by a telescope depends on the area of its collector, and so it scales as d squared. The observed intensity, the power per unit area, of a source at a distance r varies of 1 over r squared. Hence the ratio of the light gathering power of our two telescopes varies as the square as the previous quantity. Thus the 10-centimeter telescope on the spacecraft observing at a 0.1 AU gathers 2,700 times squared, that is 7.3 million times as much light as the 100-meter telescope observing at 4.25 light years from the Earth. So an interstellar spacecraft will achieve much higher spatial resolutions and light gathering powers than an earthbound telescope, which has a mirror even hundreds of kilometers in size. There are at least two more generic observational benefits of sending a spacecraft to a star system, however. One is perspective. A spacecraft will be able to view a star, planet, rings, or whatever we're interested in observing from many different angles. It'll also be able to view it with different illuminations of the host star. Such perspective changes are essentially impossible to see from the Earth. The other benefit is in situ measurements of atoms, ions, dust particles, and magnetic fields. Just as interplanetary spacecraft already do in the solar system, an interstellar spacecraft could measure these directly. This obviously can't be done from the Earth, where we only have photons to go on. Finally, if a spacecraft not only goes into orbit around an exoplanet, but drop probes to fly through the atmosphere or land on its surface, say, then we enter a whole new realm of exploration that is not possible remotely at all. Let's talk a little bit about the scientific motivations. There are various, but they could be divided perhaps into three main topics: stars, planets, and life. Observed from the Earth, stars other than the Sun are unresolved points of light. Although astronomers have nonetheless managed to learn a lot about other stars, we know a lot more about the Sun than other stars because of our proximity to it. Consequently, the Sun serves as a fundamental anchor, calibrating almost everything we know about stars, and by extension about the galaxy and the universe. By observing another star close up, we can measure its mass, radius, rotation, shape, particle winds, magnetic fields, all sorts of other things directly, and use this information to reassess our understanding of stars in general. One of the most exciting prospects for an interstellar mission is the chance to study an exoplanet up close. As of July 2025, we know of about 6,000 exoplanets, and it seems that statistically at least, most stars have at least one planet. Although astronomers have managed to learn a lot about planets through various ingenious techniques, Observing them from so far away will always limit what we can learn. An interstellar spacecraft, in contrast, could map a planet's surface at high resolution and high contrast and monitor how features change over the course of a day or year. If the planet is a gas planet like Jupiter or Neptune, or a rocky planet with an atmosphere, we can study this atmosphere, its physics and chemistry. If it's a rocky planet and the atmosphere is not completely opaque, then we could image the surface and look for mountains, deserts, volcanoes, oceans, ice caps, and other geological features. Our spacecraft can, of course, also look for evidence of life. Favorable biosignatures are chemical traces in the planetary atmosphere, examples of which are oxygen or dimethyl sulfide, DMS. Now, simply spotting such a chemical is not a sure sign of life, as they can be produced by abiological processes. So in practice, we need to identify the presence of multiple traces and the simultaneous absence of others. We can do this to a limited extent remotely, and this will no doubt improve in the future, but spacecraft will allow far more accurate and detailed measurements. Now, biosignatures are powerful, but they do make assumptions about the chemical nature of life. A more biologically neutral way to look for intelligent life, at least, is through so-called technosignatures. Examples include surface structures like agriculture, cleared land, or urban areas, as well as emission from streetlights or industrial activity, similar for images of the Earth at night. As one famous 20th century philosopher said, space is big, and even the nearest stars are a long way away, 270,000 astronomical units to Proxima Centauri. So it'll take an enormous effort to get to even the nearest stars within a human lifetime, and so we focus on these nearest stars as likely destinations for the first missions. We currently know of 35 stars and brown dwarfs lying within about 12 light years of the Sun. Some of these are gravitationally bound as binaries, 3 are in triple systems, to give a total of 22 stellar systems. These are detailed in a table in the chapter. In these systems, we currently know of 15 planets plus another 16 candidate planets, the existence, or not, of which still needs to be confirmed. This is the status as of early July 2025. There are almost certainly more planets which are currently below our detection limit, so by the time you watch this video, these numbers will quite probably have changed. Our nearest star system, Alpha Centauri, is a triple system comprising the binary stars Alpha Cen A and B, orbited by the much more distant companion Proxima Cen. I say much more distant from those two stars, for Proxima Cen itself is actually the nearest star to the Sun at about 4.25 light years. It's much cooler, fainter, and smaller than the Sun, with a mass of just 10% of that of our star. Now, Proxima Cen has at least one exoplanet called Proxima Cen B. Its minimum mass is about 1 Earth mass. It was detected by the radial velocity method, so the unknown inclination means we can only determine a minimum mass. But still, this means it may be a rocket planet with a surface. The planet orbits the star every 11 days with a semi-major axis of 0.049 astronomical units. That's 8 times nearer to its star than Mercury is to the Sun. But because its star, Proxima Cen, is 700 times fainter than the Sun, Proxima Cen B is actually in the so-called habitable zone, that region where, if the planet has enough surface pressure, it could retain liquid water. This does not mean there is water on the planet, nor, of course, that it could sustain life, not least because Proxima Cen is a very active star, but it does make this planet that little bit more interesting to investigate. There might even be two or more planets around Proxima Cen, one in a 5-day orbit, another in a 5-year orbit. We shall see. By the time we're ready to launch an interstellar spacecraft, there will undoubtedly be sufficient choice of targets. But as travel times are long, my bet is that we will still want to select the Alpha Cen system for the first mission. We could even visit all 3 stars and, as we'll see in later chapters, use them to help decelerate the spacecraft. So the chapter in this book covers a few other topics I haven't mentioned, including definitions of life and the circumstellar habitable zone, as well as a summary of the science the spacecraft could do in the interstellar medium during its journey to a star.